Thank you very much. So hi everyone, I'm Alex Owens. I work at Man Group. So I actually, just to give a bit of background on myself, I started out with a computational physics PhD in Fortran 90, which is how I learned to code, and then quickly decided to find a job in another language. So I've been working as a software dev now for 8 years, mostly in C++ and Python. And the last 3.5 years of that, I've been at Man Group in the ArcticDB team, hence the slide and the cool logo. And yeah, today I'm going to talk about why you should stop pretending your sparse data is dense. So slightly clickbaity title, but that's the world we live in. And congratulations everyone for not going to an AI talk. I know there are mostly those this week. Cool. So what do we mean by sparse data? You should always define your terms. So it's pretty vague. Any data that has some values missing for some definition of missing is what I'm going to use. But I work on a Dataframe database, a bit more on that later. So we're actually going to be talking about columnar data, so pandas, polars, arrow, that sort of world. So data that looks like this, right? So I'm going to use these double question marks throughout the talk to represent some kind of missing value for some definition of missing still. But yeah, columnar data of generally numbers and strings is what we're going to be focusing on, partly because that's what most things look like, and partly because that's what ArcticDB is specialized for. So we're going to start with a couple of motivating examples. So first one is streaming tick data. So this is the Man Group Quant Finance track. So hopefully some people have some experience in this area. But the sort of canonical problem is that you have some messages coming in from an exchange that represent some kind of financial data. So T0, T1, T2 are various timestamps. And then you have some messages coming in. But the interesting thing about this problem is that the messages don't have a fixed schema. Maybe the exchange changes its data format periodically. Maybe there's just a bug, so you get something in that doesn't match everything that came before. But ultimately, you're going to want to store this somehow, and you're going to want to read it back as something that looks like a data frame. So in this case, we have a message that comes in at T0, and this has 3 fields, right? It looks like JSON here. It's in some binary format in real life, but you've got a stock, Apple, you've got a volume of something happening, 100, and then you've got a price, $10.52, say. And then at T1, you've got another message. You've still got a stock field for Google. You've still got a volume field. But the exchange changed its mind about storing prices as floating point numbers, which can have big problems. And now it's storing them as integers in cents. So now you've got this new field, price I, which is your stock price as an integer. And then maybe at T2, you've now no longer got a stock field. They've changed their mind. Now they want to call it a ticker. It's still Apple, it's still representing the same information, but the message is not the same anymore. And you've still got a volume and your price is still as integers. So if you write that into your storage format and then read it back out as a data frame, it'll look something like this. So your stock field is missing for T2, but it's present for the other 2 timestamps. Your volume field is there for all of them. Your price is there either as a float 64 or an int 64, and your ticker is only there for your final price. So you've got a load of missing data, basically. And you need to both store and process this somehow. But that's a little bit complicated, and we can make it simpler to talk about. So here are 2 super simple data frames, and we're going to use pandas to do an outer join of these 2 data frames, a concatenation. So outer join just means you keep all of the columns from both data frames, if anyone wasn't aware. OK, so we've got a float column, a string column, a date time column, and an int column. So when we do an outer join of those 2 things in our missing data representation with the question marks, it's going to look something like this. So columns 1 and 2 have values in the first row, columns 3 and 4 have values in the second row, but nothing, and we've got these 4 missing values. So if you do that in pandas, what you get is this. So your float 64 column, this has a nan where there was no value. OK, that kind of makes sense, right? A nan is like a missing value of some description with floats. With your string column, pandas stores strings as objects, so none for a missing object. That makes some sense. For your date time column, you've got this not a time concept, which is kind of like a nan, but for timestamps, so that makes some sense. But actually, the int column isn't an int column anymore. It's a float column. So pandas, in its infinite wisdom, has decided to promote your type to a float. And so now instead of an integer 0, you've got a floating point 0, and you've got a nan where the missing value was. So you've lost some precision here if you had genuinely 64 bits of information in that integer. And that's kind of problematic, right? So even if you accept that the nan, the none, the nat are useful representations of missing data for your specific type, what if your actual data contains those values? What if, say, your float column is the result of division between two other columns and you divided by 0 and it gave you a nan? What if your string column contains missing values with nuns, right? So now when you join these things together, you can't tell whether there was a value present or whether the value was present and it had one of these specific values, and you've still got your integer column problem. So we're going to do a bit of a data structure deep dive on how pandas, polars, well, arrow really, but polars for sake of argument, and ArcticDB store data that looks like this, and what are the pros and cons of the various approaches. And to do that, we're going to just use this column as like a canonical example of something with missing data. So it's super simple. It's only got 5 values and it's got 4 missing spaces. So let's start with pandas. So pandas has been around for a long time, much longer than the other things we're going to talk about. And it's historically stored data in NumPy arrays. So you can do arrow-backed pandas now, and as of pandas 3.0, that will be the default. But you can already do arrow and other things more easily. So I'm going to focus on the NumPy-backed pandas for this example. And if you look at the buffer here, it's just got nans where those missing values are, right? In the same way as when we did our concatenation, a missing value was represented by a nan. But a NumPy array is basically just a contiguous buffer of memory, some fixed number of bytes, and a data type saying how you should interpret that memory. So in this case, float 64. So, and a nan is just a special 8-byte value. It's a valid floating point number. Just on my machine, I ran like, what's the hex output of a nan? It looks like that. It can be a few different things, but it's just another 8 bytes is the fundamental takeaway. It's not particularly special. So in this case, we've got 9 rows of data. Only 5 of them have values in. Each value needs 8 bytes, so we have a 72-byte buffer. But this doesn't change with how many missing values there are, right? So if you have a billion rows and only 5 of them have values in, you're still going to need 8 billion bytes to store that data. This also goes some of the way to explaining why pandas chose to promote the int column to a float, because there's no good missing value for an int column, right? Like pandas by default, we'll come onto it, will do a 0 for a missing value, but 0 is generally a valid integer value that you care about. You might have some application-specific integer that you know won't be part of your data set, right? So maybe like int64 max, because it's representing a volume, will be usable for you to represent missing data, but it's going to be application-specific. There's no general purpose solution to this. Pandas also has this concept of a sparse array. So I haven't seen this in the wild much, but since I was writing the talk, I did some digging and found it. So this actually uses 2 buffers to represent the same data. So you have one that's the same type as your underlying data. So in this case, a float 64, which is the data labeled column on the left here. And then you also have this index column. So this is an int32 column, and that tells you where the values were in your original data frame, right? So you've got the 0 value was at index 0, the 1000 value was at index 1, there's nothing at index 2, and then the 2000 value was at index 3, and so on. There is another representation that's a little bit more complicated, but I'm not going to go into that here. So this solves our memory problem, right? So if you have your billion values from before and it's only got 5 billion rows, only 5 actual values, then it's going to take way less memory than the 8 billion bytes we needed previously. But the random access is no longer order 1. So if you care about, what's the value at position 7, you have to effectively do a binary search through this index column to work out whether there was any value at position 7, and if there was, what value it was. And finally, you still actually have to specify a missing value. So if you've got a sparse array and you say, give me the value at position 5 in this data, it will give you something. It won't say there was no value there. So for floats, it will give you a nan. For integers, it will give you a 0. So it's still not a general purpose solution for integers in general. So what are the alternatives? Arrow is sort of I was going to call it new kid on the block, but it's been around for a while now. But it's the much more modern in-memory format than NumPy or NumPy-backed pandas. So how does it represent this data? So it also uses 2 buffers. The data buffer, again, is of the same underlying type as your original data. And now you have this validity bitmap. So this is just a true-false Boolean array saying whether or not there's a value in each position. I've called it bool1 here because it uses 1 bit per bool. It's like a packed vector, basically. So it's very space efficient for what it's doing. So this has a couple of nice properties. It maintains the order 1 random access. But actually, the data buffer is still the same size as the NumPy array was in pandas, right? So it's still 72 bytes, regardless of how many missing or present values you have. So now your memory usage is constant, regardless of how many missing values there are. So we haven't actually saved any memory by moving to this representation, but we do now at least have a nice general purpose solution that will work for any data type, because you don't have to have some like type-specific missing value representation. The question marks, that there can be any value in those 8 bytes, right? We don't care because we're never actually going to use them for anything, kind of. But memory usage isn't the only factor to think about when you're thinking about storing data, right, in memory. Also, most people will also be doing some processing on their data. So we're going to use 3 like little toy examples to play with the data structures of Arrow via polars and with ArcticDB, which does something slightly different, to sort of show how you can get more or less performance depending on your choices. So I'm going to generate 100 million row int64 column with value densities ranging from 1% to 100%. So 100% every row has a value, 1% most of them are empty. So it'll look something like this column on the right here, but with more or less missing values depending on the density. There's some specs of the machine and packages and stuff that I was running with, and that's just the code to generate it, which is just basically taking a bit set and a buffer and turning it into a polars data frame. So I'm going to run all of this on a single core to avoid sort of contaminating the effects with parallelization impacts. So the first thing we're going to talk about is a single column projection. So this is one of the simplest things you can do in polars. So you take a column and you add a fixed value to every value in that column, producing a new column, in this case, 42. So you've got your input density, your input memory, your output memory, and your time in this slide. So the input density is how we generated our data, 100%. Every row has a value, 1%, most of them are missing. Your input memory is basically independent of your input density, right? As we discussed, you still store the same amount of data regardless of whether or not you have loads of missing values or not. Your output memory, because you're just adding a fixed value and you produce a column that basically looks the same in terms of its sparsity to your input. So the output memory will be the same as the input memory. And what you see with polars is that the time is super fast. Obviously, it's polars, but it's 57, give or take, milliseconds, regardless of how sparse your input data was, right? Which some people might find a little bit surprising. You might think, well, there's only 1% of the values. Why is it doing the computation for the other 99% of the values? Let's go to a 2-column projection. So now we're just going to take 2 sparse columns and add them to each other to produce another sparse column. So in this case, actually, your output doesn't look the same as your input, right? So if you take the first row, for example, column 1, that has a value in index 0. Column 2 doesn't have a value in index 0. So in your output, that's going to be a missing value. So you no longer have this like simple relationship between your input and output in terms of the density. So if we do that in polars, so the input densities, for the sake of keeping everything fitting on one slide, I've used the same density for both of the input columns, so 1 through 100. Your input memory, that's just double what it was on the previous slide, on the previous operation, sorry, because nothing's changed there. But now your output density is lower. So you've got 2 columns that are both 90% values in your inputs. Your output only has 81% values when they're randomly generated, because you take the logical AND of the 2 validity bitmaps, basically, to produce what your output data is going to look like. Your output memory is still constant because there's no memory savings to be had by having sparse data. And your timings, again, are pretty constant, a little bit slower than the single column projection. But the performance is totally independent of your sparseness of your data. And now the output sparsity is even more, right? So there's even fewer computations that you did that you actually cared about the result of. So what's going on here? So the way that Arrow stores its data, as we showed back on this slide, means that when you're doing computations, you do the computation across the entire data buffer, and you just use the validity bitmap after the fact to basically fix like which values you actually cared about. So you don't have any savings from the fact that you don't actually care about most of these values. And that's for both the 1-column and the 2-column case. And the final little test case we're going to use is a single column aggregation. So in this case, we're just going to sum all the values in a column. Super simple. Again, the performance with Arrow is independent of your sparsity. So this actually is a little bit more complicated now because you can't ignore the fact that some of the values in your column are missing. Because if you add those into your result, then you'll just get the wrong result. So now you actually do have to take that into account. But the way that it works, clearly, it doesn't have any impact on the performance. It's still 30 milliseconds. OK, so coming on to what I work on. So ArcticDB, what is it? So it's a high-performance Dataframe database. It's sort of focused on time series, although it's pretty flexible. You can store pretty much any data frame in it. It was developed at Man Group, started about 7 years ago now, but it's been available on GitHub for 2.5 years. It's a client-side database. It's Python API. It's pandas in, pandas out. So you take a pandas data frame, write it in, you read it back out, possibly after doing some processing, and you get another pandas data frame, although we will be adding Arrow support soon. So it actually has a lot of the same challenges, right, as pandas and polars. Like we have some processing capabilities, nowhere near as sophisticated in terms of the breadth of support as pandas or polars, and definitely nowhere near as sophisticated as polars when it comes to things like vectorization and performance optimization. But we have some. So we can still do some comparisons, if not in the absolute time, in terms of the relative time, based on the choices we've made of how to store sparse data. But in addition to the challenges of processing the sparse data, we also have to store it on disk, right? We have to serialize it somehow because you still want to get the same result back that you wrote in. So in terms of ArcticDB's on-disk representation, it kind of looks like a cross between the Arrow and the pandas sparse array format, right? So we've got this data column, which is only the values that were present, the same as the pandas sparse array. And then we have this validity bitmap, which is basically what Arrow had. So when you're going to compress something like this, it's actually quite important to have the float64 column not have all of the missing values in. Because generally, if you pass that to some kind of compression technique, it will say, OK, you've got a load of missing values. I'm going to run length encode those. But you're not actually going to get compression amongst the values that are in the actual column. And that's a real disadvantage when it comes to things like time series data, where frequently your values will be strongly correlated with each other. Let's say it's like the price of a stock, right? That's relatively slowly changing over time, unless you're NVIDIA. So you get a lot better compression by storing only the values that are present for this. And then for the validity bit set, I've just put like compressed and without a number for that because we actually use a library called bitmagic to serialize that bit set, which I'm going to go into a little bit more detail on. For reference, because they're kind of the closest thing that people have heard of to ArcticDB, Parquet does a very similar thing if you've got sparse data. So it'll use an int16 column for the validity bitmap, but that will only have a 0 or a 1 in, so that will compress really well, easily. So in terms of serializing, you might think that sort of the best you can do with a bit set is what Arrow has, right? You've got 1 bit per bool. That's when you've got totally random noise, that's going to be the best you can do. But if there's some structure to your data, actually people, particularly the guy who writes bitmagic, have put a huge amount of thought into how you can more efficiently store that. So in this example, I've taken 100,000 row bitmap, just because that's our standard on-disk segment size. And the bits are randomly 1 with the probability given in the value density column, or 0 otherwise. So the bool 1 memory for that, the Arrow representation, takes 12.5 kilobytes regardless of how dense it is, because it makes no difference, right? Whereas bitmagic is able to do better than that. So if you've got a 50%, like 50-50 zeros and ones, then it falls back to clearly the same representation. But if you have more structure where you've got very sparse data, so 1 or 99%, it's able to do a lot better. It can generate sort of 10 times the compression ratio of just storing the buffer as is. But actually, a lot of time series data doesn't look like that. You don't have totally random noise in terms of where you have values and where you don't. What you generally have is runs of values followed by large runs of missing data. So the most extreme version of that is where all of your on bits are at the start of your buffer and all of your off bits are at the end, right? So if you take that and compress that with bitmagic, all of a sudden it doesn't take almost any space at all. It's 1,000 compression ratio, because all it's really going to store is the length of the run of ones at the start and the length of the run of zeros at the end, and nothing else. OK, how about in memory? So the ArcticDB in memory format is, again, it's a bit of a cross between the pandas sparse array and the arrow validity bitmap. So we've still got only the values that were actually present stored in the data array. But now I've got bool question mark because it's bitmagic's internal format, which is, it doesn't have like a nice mapping of exactly how many bytes you need to store each value. But it uses what's called a rank select bit vector representation. So it's slightly more memory than a bool 1. It still has order 1 access, so we're still better than the pandas sparse array in terms of that access. But it also has this nice property that you can really efficiently iterate only true bits or only false bits. So what that means is if you're doing something where you just care about indexes where the value was true, you can do that in order 1 time as well. But what you can tell from this representation is that the data buffer memory usage now scales with the number of non-missing values. So if you have your billion row column that only has 5 values in it, now we only store the 5 values in the float buffer plus the validity bitmap. But the in-memory representation of bitmagic is quite similar to its serialized format, so it will be much more efficient than the sort of 12.5 kilobytes we were seeing before. So we'll do the same computations we did with polars in ArcticDB and see where we're faster, where we're slower, what the differences are. So the first one, super simple, where we just add 42 to all of the values. You'll see some differences in every column, really. So the input memory now scales basically linearly with the input density of your data plus the overhead of the validity bitmap. So we're using way less memory to store the same thing. And the output memory, similar to Arrow, it's the same as the input structure, right? So you do your projection, you copy your bit set because it's the same for the output, and you get the same memory saving in the output. And then in terms of timing, what you'll see with the fully dense representation is that we're about 3 times slower than polars. Like I said, we're not anywhere near as sophisticated as them when it comes to our processing capability. But what you also see is that we scale not quite linearly, but we scale with the density of the data, right? So the fewer values you have to do the computation over, the less time it takes us to do that computation. So what you end up with is that while we're slower than polars for the dense case, at some point there's a crossover where it gets faster to do it in Arctic than in polars because we're taking advantage of the sparsity of the data when we're doing the computation. Now, what about the 2-column projection? So as I said before, the output validity bit set is now the logical AND of the 2 input validity bit sets. So the input memory, again, scales about linearly with the input density. But now your output density, and therefore your output memory, scales with the square of the input density. So by the time you're at 1% dense 2 input columns, your output memory is basically just the validity bitmap and the few values that you're left with. But in terms of timing, so for the fully dense case, we're, again, about 3 times, 2.5 times slower than polars, fair enough. But what you actually see is that the timing jumps up straight away as soon as you have any missing values. And that stays pretty high down to, in terms of the numbers I've taken, 50%. And then it starts getting faster again as it gets really sparse. So what's going on here? So there's no free lunch. The memory representation we have means that the algorithm to compute the sum of 2 columns is much more complicated. So you have to be tracking where you are in each of your sparse columns as you iterate through, which basically introduces an if statement into your tight loop, which will always kill the performance. So there's no free lunch, but what you do see is that if your data is sufficiently sparse, even this more complicated algorithm is faster. So in the case where you've only got 1% of values, because we're only actually computing the sum for those 1% of values, it gets much, much faster. And finally, the single column aggregation. So in this case, the input memory again, oh, I've copy and pasted the wrong input memory column here. It's scaling down linearly with the input density. And in terms of timing now, the algorithm is super simple for us, right? So we don't store any of the missing values in your data column. So you can literally just rip through it, summing everything up without any logic whatsoever. My guess is that the compiler vectorized this for us because it was so easy, which is why we're even faster with the fully dense case. But again, it scales linearly with the number of present values you have. So as you have sparser and sparser data, it takes less and less time to perform this aggregation. So we actually maintain this memory format all the way through our C++ layer. And it's only at the edge when you get to the Python layer where we're going to give the data back to pandas that we change to their representation. So all of our computation and our memory savings apply all the way until we're going to give the data back to the Python layer, at which point we have to convert to something that one of these libraries understands. So with pandas, that's the dense memory representation with some type appropriate missing value. We are adding arrow support soon, so you'll be able to basically read directly into polars or PyArrow or whatever it is that you're using. And then eventually we want to get the best of all worlds, where there'll be some things where we're faster because of our in-memory representation and our sort of increased knowledge of the on-format data. But for everything else, polars is, king of speed basically at this point. So we're going to be able to stream data directly from ArcticDB into polars. So that for anything that Arctic can do, Arctic will do, but without you needing to know or care whether it's Arctic or polars doing the computation, it will give you the right result out the other end. So conclusions. A lot of real-world data is best represented sparsely. Ignoring this can cause some type-specific pain, particularly around integers. For very sparse data, you can have really big memory savings and, depending on the computation you're performing, maybe some performance benefits to sort of taking advantage of the sparsity of your data. But there's no free lunch, and sometimes maybe you should treat it as dense, even if it is sparse. I think I'll probably go away and add some heuristics now to make sure that we're not as much slower in the two-column case, for example. But you only find these things out when you have to write a talk for it. So, thanks. All right. Thank you.
Our next session is keeping